I'm David Lazar, for those of you who don't know me, and I'm very pleased to welcome James Wilson, who's come all the way from sunny San Francisco, sometimes sunny San Francisco.
I hear the weather here is really nice right now.
Yes, well,
this is beautiful.
Yeah,
I've gotten way too used to warm weather, though, I have to admit.
Well, the steely gray is what we do.
But
so
it's great,
yeah. Actually brings back memories of Ann Arbor. So. But in case, very pleased to have James come here to talk about his research is focused on the statistics of complex networks. And he's going to look at one angle of that today, which is looking at, in particular, community intersection multi-layer networks, which is something actually very relevant to many folks here at the Institute. So particularly fortuitous that we were able to snag you for this visit. Also, by the way, I want to thank Single Out Summer for facilitating this, and helping. And for those of you coming from political science, it's great that we're also bridging political science and network science in this event. So with that, James,
Thank you so much. Thank you, and thank you everyone for coming to this talk. So I hear you've been going on a really strenuous job talk search recently, right? About 9 or 10 different folks, so I'm still happy to see that the room is quite filled. Thank you for introducing me, and I'm incredibly excited to be here. So as David pointed out, I am a statistician by trade, but I think networks all day. I mean, this is my research area. This is absolutely something I'm interested in, both from a statistical standpoint, but also from an application standpoint. I am at the University of San Francisco, and yeah, so I hope what I want to do is open this up for questions as we go along. So I mean, I enjoy the back and forth, so please feel free to ask as we go. So just a little bit about me. So just giving you a brief idea. So I went to, my undergrad's actually not up here. I put my graduate schools and then where I work. But I went to Clemson University when I really started getting into mathematics and statistics. At that time, I didn't know exactly what I wanted to do. I was either going to be an engineer. I was thinking about chemical engineering at that point, but decided, statistics. I took my first stats class and fell in love with that. And I'd always liked networks, and I had an advisor there that I worked with on my master's thesis who had a nice network problem using the EM algorithm, and I really got interested since then. Now I say that I make every problem a statistical network problem since 2012. That was actually my second year as a PhD student, so I graduated in 2015, and I did my PhD at the University of North Carolina at Chapel Hill in the Statistics and Operations Research Department. Now I'm at the University of San Francisco and tied to a big part of what's called the Data Institute there. So another thing that really interests me about the Network Science Institute, first of all, it's one of a kind. And if I could have had such a thing in San Francisco, I absolutely would have, but there's a lot of tech, a lot of data science there, of which networks definitely play a big role. But anyway, we have the Data Institute, which started a year and a half ago. I take a big part of that. I'm an associate director of research there, and then also director of the data science program. So I'm always happy to talk more about that if you're interested. And I always like throwing out my favorite picture. This was kind of my first, at least nice-ish looking picture of a network. So you've all seen networks, and the first few slides that I'm going to show you, I can already see, your visualizations are much better than mine, so don't mind me, but I tried my best here. But no, this is actually my personal Facebook network, whenever it used to be possible to collect these things, right? So this was back, let's see, when did I actually get this? I think I got this data in 2014, and that might have been the last year that you could actually crawl and get your friendships, or the friendships of your own friends. And what's really funny about it, so community detection, the reason why I love working with community detection is it's an exploratory method that really allows you to see things that are happening in this otherwise hairball of a system, right? So here, in this Facebook network, the main idea that I found here, I went back and actually hand labeled where I met each person. And now the colors in this are not actually according to the clusters, but actually according to the true labels that I labeled them. And so here what we have is, this was my high school, so where I met folks from high school, and then in undergrad. And so in high school was when Facebook came out, it was in I can't remember now, 2014, right, I think, or something long. No, I'm
2004.
2004, sorry, I'm off my head. 2004. So I graduated in 2005, and so this was certainly, everybody was like a tightly knit group and really wanted to be on Facebook. This was now my undergrad, and what's interesting is you can start to see points that have an overlap. I know it's a little bit of a small picture, but this was one person that also went to the same grad school as me, so we shared a lot of friends both in undergrad as well as in grad school at Clemson. This was my second grad school, and so at UNC, and then this red here that you see are people that I actually worked with when I worked at a drugstore for 4 years for my part-time job. And then finally, on the outskirts, there is a familiar color. I labeled most of these people as acquaintances, actually. So it was one of those things where, I don't know if you're like me, but if you go back to your Facebook or LinkedIn or any other social media site, you'll probably go back and be like, I don't know who this person is, right? So that happens often. So I labeled them as acquaintances. I met them through someone. And actually, it turns out, a large part of what I want to look at with community detection is saying, well, you know what, there are these densely connected clusters where people actually belong, but more than that, there actually is this, what I like to call background, right? So there's this idea that there are some nodes that perhaps belong to no community, or to kind of an extraneous community. And so part of what statistics can do can allow you to actually try to assess whether or not a community really is a community, right? And so that motivated a lot of my PhD work and thinking about kind of significance-based ways of looking at communities. And that extends a little bit into multilayer networks, which I'll be talking about today. So I certainly don't need to go through these slides. You all know this quite well, but just to quickly do it. So networks, as you know from things like Facebook and other social networks that make beautiful pictures like this, it's a means to visualize and model interactions of a complex system. And here we're just going to treat an actor of the system as a vertex and place edges between actors that interact. And mathematically, we think about it as a mathematical object where we have vertices and edges. And in this case, I am thinking about unweighted graphs for the moment, though most of what I talk about can also be generalized to the weighted setting. And so we're going to be thinking about these adjacency matrices as well. So AUV meaning there's an edge weight between nodes U and V. And then we can look at the degree. So this will be an important component of what I talk about later. Just to remind everyone, it's just the number of edges incident on a given node. Okay? So I know I go by this quickly because you guys certainly all know this. And then community detection, right? So just a brief summary is to really, it's the algorithmic organization, or clustering, of nodes of a network into densely connected subgroups. Right? So clustering's been around for a long time. Community detection now has been around for a long time, a little over almost a decade and a half, at least, depending on how far back you want to go. If you think about spectral clustering as community detection, that's even longer. But the idea is to take, when you usually observe your first graph, this nice hairball that's black and white we really know nothing about, right? And then we want to do something to this to find structure. So we're looking for structure in that graph. And then maybe we can visualize, and I see it, again, all around me, and there are nice pictures of how exactly to visualize these types of communities. And so the main informal idea is to identify some subsets of the nodes such that the edge density within the sets is large and the edge density between them is quite small. Now, I call this informal, right? Because really, it's not settled upon exactly what is the correct way of defining what a community is, right? And that was another thing that kind of got to me as a grad student in statistics, is saying, well, why can't we come up with a formal reasoning as to what exactly a community is, right? So I always put quotes behind when I say large and small, because then I start thinking about statistics, right, just immediately. We need a reference distribution. We need something that we can compare across different sizes. But my main focus here is going to be multi-layer networks. So I want to extend this some because I worked in single layers or static networks for quite some time. But really, of more importance today is really what we, is thinking about multi-layer networks as well as dynamic networks and these kind of intricate layers or relationships that can happen through many different modes. So in this way, just for simplicity, I'll keep referring to a multi-layer graph just as an unordered sequence of M networks. All right, so we're just going to say we have G1 through Gn. And what's interesting about this, I want you to know I'm saying unordered because I'm not going to care about, at the moment, any time or any kind of other component underlying the sequence itself. But of course, you could think about how to start extending what I'm going to be talking about here. So for now, we're just saying we observe a sequence. And in each case, GL now is just going to be our Lth layer. And I'm going to assume that we have the same node set. So we have this bracket n is just shorthand notation for 1 through n. So we're just labeling them 1 through n. And each layer, though, has different edges. Right? So we'll call that EL. So there's an edge set corresponding with each layer. And this will describe the relational structure of layer L. And then each layer here represents a relational type or sample. So we can imagine, well, and I'll give some examples in a second, but we could imagine thinking about samples from a population. So very much so from a statistics standpoint, we say, well, there's not just one network, there's actually many networks, maybe an infinite number of these types of networks. How could we possibly look at just one of them when there's actually a sample of things that we can learn more from? And I'm going to treat vertices as registered. You don't have to do that, but I do it for simplicity of interpretation. Though I would love to hear your own thoughts on how to go about it from not. I mean, if you don't have registered vertices, and by this I just mean that vertices all represent the same thing, right? So the same type of unit. So it's a little bit of a simplified structure, but at the same time, these kinds of tools that I'll be talking about can be extended. And so some nice examples, we can think about social systems where the unit, so the node itself may be people, and interactions could be different types of Facebook, Twitter, or if they're colleagues, whether or not you're at the Network Science Institute. We can think about transportation systems where the unit is a city, and then the interaction might be, is there an airline flight between the two cities? Is there a bus route? Is there a taxi that takes you from one city to the next? Or we may think about genetic networks, which was kind of my first dive into thinking about networks was actually with genetics, and looking at breast cancer research at UNC. And the unit here, you can think about our genes, and the types of interactions we may have include different types of measurements that we can have on genes, like the copy number, as well as mutation type. So is there a mutation associated with that given gene? Or just the overall gene expression. So what's kind of looked at often in microarray analysis. So, and I want to emphasize something here too with multi-layer graphs is actually what I'm calling layer heterogeneity. And by this, my main emphasis, my main mantra that I want to go with here is a community structure need not be the same across all layers. Okay, so we could have all of these different systems with many different types of interactions. But in my mind, there's really no reason to say that the community structure will be the same across each one of these layers, right? And so we'll consider heterogeneity, and you can think about this in many different examples, and we'll look at two in particular. The first one, which I should have put this one last. I'm not going to look at this one today, though this is a main motivation of my work these days, is working with brain networks. Actually, with the guy Skylar Cranmer at Ohio State and some other folks there, some other neuroscientists. And so what's interesting is with brain networks, we can look across typically developing adults versus, say, football players who have suffered from a concussion. So you may in fact have differences within these brains, right? We wouldn't assume that the community structure, so if we're looking at the actual structure of how voxels interact with one another inside of one's brain, you wouldn't expect it to be the same across someone who has an ailment like a concussion or stroke or some other medical condition as you would for someone who hasn't had this type of interaction. So there would be heterogeneity there. You can also think about, and these bottom two examples I will actually go through as applications, airlines that travel in Eastern versus Western Europe. So we could just look at the airline system of transportation and try to understand exactly what communities are there of either airports or of airlines. And then we can also look at social media, so used for different purposes. So we're probably going to have different communities depending upon if it's a professional relationship versus if it's a personal relationship, right? And in many cases, people actually want to make completely opposite friends in those, or different opposite acquaintances in those types of situations. So if we tried to look at that community structure together, we're going to lose a lot of information. So in social networks, one example that I'll look at, it's a simple example, but it's good for showing exactly what I'm thinking about with social networks. And one is the Australia CS social network. So this was actually, it was a survey taken at a CS conference in Australia, and there were 5 different measurements taken on these attendees of the conference, and they were as follows. So you would ask among everybody in the group, were you co-authors with it? And so you could make a graph out of this. You could say, did you spend leisurely, or have you spent leisurely time with them at the conference? So meaning maybe out for drinks or something like this, or out for a restaurant, not to talk about work. Have you actually worked with the person? And did you go to lunch with them? And then finally, are you Facebook friends with one another? Right, so 5 reasonable questions that you would think would have some overlap amongst what's going on here. But we can see even just by plotting, this is with no structural reorganization at all, right? So we're just putting the graphs down. Don't really tell us much from this, but the immediate thing you can see is that there's at least degree heterogeneity, right? So there's at least some sort of sparsity differences. So co-authors, there's way fewer co-authors than there are folks who share Facebook with one another. Looks like work and lunch were kind of the top 2, or the most dense networks to consider. And that sparsity can tell us something, right? So that can actually give us more information about the layer itself. Another example, which we'll go into, is the air transportation network. And this picture is not my own, but it was in the recent multi-layer network review paper by Covariant et al. And in this, what we're looking at are different airlines. So now the actual layers are represented by airlines. And we have cities as the nodes. And we put an edge between them if you fly from one city to the next. Right? So each layer is just saying where exactly do each one of these airlines fly to. And in this case, you wouldn't expect that the community structure across these layers look the same either, right? Because there are certain airlines that are going to go to some regions versus others, right? And we'll look more into this, and I think it's quite interesting what we end up finding. But this data set, so it was actually published in Science in 2012, and it was looking at European air travel on June 1st, 2011. So they just took a snapshot, a one-day idea of what's going on with these numbers. Well, the key point is air travel, among other types of transportation networks, is going to be heterogeneous. So I guess I'll pause here for a second and ask, are there any questions thus far? So it's all been a little bit of an overview, but I'm happy to answer anything as we go. All right, are you motivated? Are you excited? Do you think networks? Ah, yes, question.
So I noticed that that's a cursory analysis of the graphs you put up. It looked symmetric, undirected.
Right.
And I would think that what about the airline networks? Are you going to treat those as directed or undirected?
Ah, great question. Let's see. So in this airline network, we do actually treat it as undirected, though I believe the original network is directed. So you're right. I am treating things as undirected here. Maybe that's not the best idea, but yeah, that's a good point. Other questions? All right, so far so good. So everybody's motivated. You can get the idea that layers are heterogeneous. All right, that's great. So now let me actually go through and talk about, I'm going to label them as 3 different types of kind of multi-layer community detection methods, right? So, and now this is my own labeling, so this is at least in my publication, but at the same time, we can argue about what other types you want to include here. But I think this does a pretty good job of kind of summarizing up to this point. In many ways, so the big question with multi-layer graphs, this is a more complex system than the complex system of a network by itself, right? So we're interested in, now we have layers, we have many different graphs, and how can we incorporate the information across these layers, right? And so here the big question is, well, what is a community? I mean, that's even a hard question for a static graph, right? It's not well settled upon. I mean, folks have certainly settled upon something. Generally, they go along the lines of modularity or something along these lines, maybe a likelihood-based inference. You could look at many different types of things. Perhaps it's you can look at spectral clustering as well. But that's a question in and of itself. But let's just even step back further. What do we even mean by a community in a multi-layer graph, right? And then, of course, if we can come up with a definition of what exactly is a community, then how do we go about identifying them? And so, in my own thoughts, there are really 3 general approaches here. So one is kind of an aggregate approach, which may seem like the most natural, where you're just going to take the layers essentially and just squish them into some average or some sum of these adjacency matrices, and then just say the community structure we find on this sum is indeed the community structure of the entire multi-layer graph. We could also look separately. So separate analysis would just be, okay, there's no joint structure among these layers. Let's just treat them all separately, come up with our communities, and go from there. On the other hand, and this is my favorite descriptor, there's super adjacency matrix methods. And I don't remember where I read that term, but it is one of my favorite ways of thinking about a multi-layer graph is through its super adjacency matrix. It just sounds like a cool way of going. Anyway, it is useful, and it's actually one of the more popular ways of going about this, though you may not have heard that term. So let me, yes?
So I guess a question I have here, when I see a question like, what is a community?
Mm-hmm.
And I'm thinking more social scientifically, it's, even let's say within the social science literature, it'd be like, what's the social foci around where relationships are built? And so part of it, I guess this is more of a statement for a reaction,
Mm-hmm.
but when we think of these methods, these statistical methods embedded within a particular set of phenomena, like let's understand a community, which in itself is actually, the popular parlance would be referring to people in a community with a set of characteristics.
Mm-hmm.
That what is there? are the, what's the mapping, let's say if we're thinking in a social science area, like, are we thinking of this just as a statistical abstraction, or do we start with certain phenomena around which we then build the statistical thinking?
So I really like that question, and I think this is exactly the way that we need to honestly take these types of networks. So in many realms, I think, I'm going to say in practice, often what happens is there's not too much thought that goes into actually what these layers are. They just start analyzing, right? So there's kind of, okay, let's just analyze them, see what we can get out of it. And then kind of reflect back, right? So then they'll say, oh, there was a social science way of looking at this, does it match, right? And I know from a methodologist standpoint, a lot of folks do that. But I think what's really interesting is you could start, and there is some research in this area, very recent, trying to motivate exactly what a community is, not just based on structure, so not just the structure of the graph itself, but also based on kind of features of that given layer or features of those given nodes, right? So just as there is the exponential random graph model for kind of other types of structure, it's actually statistically analyze that. We can do the same thing for, or a same type of analysis for community structure as well, but defining that is still a challenge. So where I'm going to go about this today, though I love the question, I think it's exactly where we need to go with it, is just looking at structure and structure only. So I'm not going to be thinking too much about the actual labels for each layer or each node, but that is it's something you can incorporate. Yep. Yes?
Going off of that, and maybe I'll get to this, but given how much of like identifying a community is based around like the weight of the edges, essentially, do you identify like linchpin nodes? Like the ones that have the most connections with their community as a way to analyze the structure?
Oh, that's good. So in a way, there are ways around, well, so there are a few things that could happen. So for those that have a really high degree, right? So in a way that could start to take over all of the information, right? Because just going back to this example. So, well, I actually don't see specifically one person that has a high degree, but you could imagine, let's just say that we had a row slash column that was really densely filled, but everything else was quite sparse. Right? Then almost all the information we can actually get about that graph really lies in that person who has a very high degree. And that causes issues with traditional ways of looking at those. So there's certainly a way around this would be to incorporate kind of this degree heterogeneity through things like the degree corrected stochastic block model and through other models like that. But now, so to your point though, I think what you're asking is like, how do we now kind of validate what we find? Is that the idea? So for validation, I think it depends on the domain. And I hate to do that because it's one of those things I'd love to give you an exact answer, but I don't know that there is. At least in brain data, right? So something I'm really interested in going more into, what you would look at are clinical outcomes associated with this, but then also relating the functional regions that you identify as a community back to now the actual structural communities that you would identify, and that people know more from white track matter and things like that. But I think it depends on context.
Yeah, I think the thought was more if you're trying to determine like how these layers actually function as a community, identifying key points, and then what would happen if you remove them with.
Oh, if you remove them.
analyzing function.
Interesting. That I haven't played around with that, but I think that's a good thing to try. Yeah. Let's talk more about it when I get to some results and tell me what you think. Yeah. That's interesting. All right, so that's kind of our motivation. Here are the three, and I'll go through this briefly with some pictures just to make sure everybody's on the same page. What you can imagine with aggregation, as I was saying, you're just going to seek vertex communities. And again, the focus is on structure here, right? So we're not really incorporating covariance from each layer or each node. And so we just take an average or an aggregate weighted network. This is a very common approach. What you do, right, is just take these three graphs, average them, we get our G bar, say, and then we come up with community structure. But the unfortunate thing about it is that you're assuming that each layer has the same community structure. And that bothers me some, because again, I was trying to motivate you with heterogeneity. I really do believe that there's heterogeneity, no matter what system you're looking at. You hope that you can find the layers that are similar, right? So maybe that should be the first task, is actually to find the layers that are very similar, and then run an aggregate method. However, one thing about it, it has really nice theoretical properties, right? So if you start going into averages, you're in central limit theorem land, right? You can do anything you want. And the same is true with spectral clustering. So if you assume same community, you're gonna find it because you're getting more information by building up layers, right? And I mean, it's funny because I think statisticians and physicists have different ways of proving the same thing, but they're all there, right? It's either eigenvalues or central limit theorems. That's all we're doing, right? I mean, in that kind of analysis. So just as a point, like that is, theoretically speaking, you can prove a lot of stuff here, and you can actually, I mean, but you have to make a really strong assumption that there is no heterogeneity. So we have to get around that. So I'm trying to get around that. So my theory is a lot harder. No, I'm just joking. but no, the theory does get really difficult if you assume that there are actually different communities, right? And it depends on how sparse each community actually is. Okay, but all that is to say, you're going to get a single partition of vertices, and at the end of the day, you call that your communities. By the way, I want to make sure on my time. Can somebody let me know when I have 15 minutes? Okay, thanks. Cool. So, because I feel like I'm only on slide 13. We're halfway done, huh? All right, let's see what I can do.
It's too engaging.
That's what it is. That's what it is. So, okay, separate analysis. So, okay, exactly what we said before. Now we're just going to treat them each as their own graph. We get a partition associated with each graph, and then somehow combine that information. So either you just treat it separately and you leave it alone, or you somehow now merge after the fact. So kind of finding, in data mining terms, this would be kind of common set, or well, now I just forgot the name. Never mind, I forgot the name. But the idea is to take these partitions and then merge them after the fact. But that avoids the kind of joint structure. Super adjacency matrix. Reason why, and I'm going to keep calling it this, is you take these graphs and then essentially put it inside of a really large adjacency matrix, right? So we're going to place each adjacency matrix along the diagonal of a much larger system. And now the thing I'm not showing you is what about between layer edges, right? And so there are some choices there too. So if you look at kind of the modularity maximization type procedures, then there's a resolution parameter. There's a parameter that is associating what does it mean to have an edge between these layers, right? Between two nodes. And there are some natural ways of doing that, but there are also some not so natural ways of thinking about that too. Okay, at least to me, this can be a little bit difficult to interpret because I don't really like saying there's an edge when that edge doesn't mean the same as an edge inside of the node, right? So you're kind of mixing two things. But we can argue about that because I know a lot of people use that type of method as well. So in our approach, what we're going to be looking at is multilayer extraction. So I'm going to kind of step back a little bit and not just identify a partition, but rather I'm going to start trying to find local sets. All right, and in fact, I'm going to be saying I want to search for densely connected, vertex layer pairs. So now my result is not just going to be a collection of vertices, but rather it's going to be a collection of vertices cross now a collection of layers. All right, and so what we hope for is that the collection, so say we're looking indexed by kappa, our vertices, so we have our vertices B and our layers L, and the vertices are going to be densely connected across the layers L. All right, and so the idea is we want some sort of significant vertex layer communities. And in doing this, what we're stating is that there is possibility for what I'd like to call persistence, right? So we want to see that a vertex community persists across a subset of layers, but we just don't know what that is without further exploration. So the idea with the same picture would be to do the following, right? So we take each one of these graphs, and then we try to identify, and I haven't shown you the algorithm to do so, but you try to identify these communities, say B1 here, which is a subset of vertices, and it shows here, cross now, B1 would be cross L1 and L3, right? Whereas we may have this other small green community that is, let's call it B2, which is across layer 1 and layer 2. So our overall community is going to look something like this. So we'll have B1, 1, 3, right? And then B2, 1, 2. And this accommodates layer heterogeneity, right? And it tries to incorporate some dependence among these layers. And it does so, though, by borrowing strength in the algorithm. And I'll show you that in a moment. But are there any questions so far? So this is kind of redefining what a community is. I'm looking at it as a vertex layer community rather than just a vertex community. Okay. So the four main ingredients here is the way I go about developing an algorithm for such a thing is with, first of all, a null model. So this is kind of the first step, right? We need a reference distribution of some sort. And so we use a random graph model for this. Then we have a statistic that measures the strength of connection within a given community. And then we'll have a score now, which is just going to be a comparison of the observed statistic to the reference distribution. And then finally an algorithm to identify communities with large scores. And obviously, anybody can come up with these 4 parts, but then the main question would be, is it any good? Right? So we want some sort of empirical justification. But more than that, we also want, are there theoretical properties of this method as well? So we can think about things like the consistency of such identifications. Yes?
So can a node belong to multiple communities? And
Yeah.
even within the same layer, it can belong to multiple communities?
Yes, that's correct. Yeah, so we're being very flexible. So I didn't show it in that, but it can overlap, and not only that, but not every node or layer needs to belong to a community. Yep. So it can be hard to interpret, well, not hard to interpret. Many times, what I've found in practice is if you go to, say, a geneticist, and they're like, I want a partition of the data, right? One thing I'm telling you is this does not partition the data. So this is giving you subsets, which sometimes can be harder for a practitioner to understand, and I totally get that. But I think it's fruitful, or can be. Anyway. So the random graph model that I consider here is the configuration model. And so I guess I want to ask really quickly, since I'm running out of time, I want to make sure to get through a lot of material. How many people are familiar with the configuration model? Kind of, sort of? All right, I'll give a brief understanding of it instead of going too much into this. It's a combinatorial model, but the basic idea is that we're going to essentially assume that we have a distribution of graphs that have the same degree distribution, right? And subject to that, there is no preference for forming a community. So it acts as a null model for a graph that has the same overall degree heterogeneity of your original observed graph, but now we can start to compare the actual community structure that we identify with this configuration model to see how well or how strong is our given community. And this is exactly the null model that's used in modularity, right? So when you see, well, and I'll show you that in a moment, but when you see modularity, which you'll see in just a second, you'll see where the term comes in from the configuration model. So it actually gives a really nice representation of what we expect, right, under the null. And so here, the multi-layer null is, we're just going to say we have a degree sequence D, which is now the degree over all of the layers. And then we'll just assume that we're going to get a configuration model from that configuration model. So this now M-dimensional or M-graph sequence of configuration models. And here we get that each layer now is going to approximately preserve the actual degree sequence of layer L. And each one of these, though, and this is important for future analysis, this is treating G at L hat, so each one of these random graphs is independent as well. So we are treating these layers as independent, and then we want to go back and identify common structure. But it would be even more interesting, so if you could do dynamics, right, to say how do we actually incorporate dynamics between these types of graphs. And so the idea is to use this distribution to compare the structure of our actual graph with now our random graph generated through the configuration model. And you do that through modularity, right? So this is kind of the classic way of going about this, which I know now, maybe if you hadn't heard of configuration model, you've heard of modularity. All right, I think everybody's probably heard of modularity. And so the configuration model serves as our null model here. And so what you can think about is if we look at the modularity now of a group of labels, so say we have C1 through Cn, which take on values 1 through k, then we're just going to get the following value. So we get, it's just normalized by the overall number of edges. And then we take each value that we observe, AUV, and subtract off what we expect now under the configuration model. All right? And so this is for a single layer network, right? But this works the same way. Oh yeah, we're going to count this only if the community labels for U and V are the same. So we're just looking at all pairs that are in the same community and then saying how much more is what we see than what we expect. Okay? By the way, this is very related to a chi-squared statistic for those that enjoy statistics. Like it's kind of fun. It's not squared, obviously, but we're doing the same thing. We're just taking observed minus expected. Right? And what you can imagine, so in just a simple setting, so in just a static network, we can write this and think about assortativity, right? So we could just imagine this is written as now the sum over 1 through k, so we're just looking at all the communities, of some delta I, or delta I is this nice sum here. And what we generally say is that when delta I is positive, so whenever what we see is greater than what we expect, then we're going to call that community assortative. Right? And then we'll call it disassortative if it's less than 0. So meaning we expected more than what we actually saw. And then finally, equals 0, community I has random connections in some way. And so we're going to call the partition assortative if delta I is greater than 0 for all communities. All right, and so the whole idea is that community detection methods, especially those associated with modularity, are looking for assortative communities. So we use this modularity now as kind of our score for each collection that we think about. So if we look at it in a more local setting. So here what I'm saying is, well, we're going to end up having a lot of vertex layer sets that we'd like to see how strong are the connections among that group. And so here we define a set modularity for each layer in L. So take this as our layer set, and then we're going to now look across the layers in that layer set. Sorry, this shouldn't have brackets, just an L. And then we can measure the overall set modularity for the given layer simply as what you'd expect. So we're going to normalize by the total possible number of edges, and then we're going to take the modularity value that we have here. So for every pair of nodes in B now, we're just going to look at that and say, let's take our actual observed value and subtract what we expect. So it's local because we're focusing only on the nodes inside of this collection B, right? And also, moreover, we're only looking at the layers that are inside of the collection L. So here we are scaling by an n term. We end up showing this is the correct thing to do, but we had to do some work to be able to prove that. It's a real maybe 12 pages of work to show that n should be there. That's tough, but it should be there, I can tell you that. And I can show you theory later, but anyway. But the idea is this is very closely related to what Klaus said in 2005 called local modularity. And so we seek communities that are assortative, thus we're looking for vertex sets such that QLB is large and positive for all L in your given layer set. Does everybody see that so far? Feeling good about it? 17 minutes left, I think we can do this, all right. So then our score is just simply to average, basically to average across the square of the sum of these things. And again, this took some work to show why the square is the right thing as well. But again, that's the theory that we had to build in, is to say where did our score actually come from. But here what we're going to say is once we have a collection BL, we're just going to measure the overall multi-layer score, so the strength of connection there, with the following values. So we're just going to add over all of those QL and B, and this positive now is just saying take the positive part of that. We square it and divide by L. Or this is the size of it. And so here, large values signify densely connected communities, and what we end up wanting to do is to seek vertex layer sets with a large score. And if you really want to think about this from a testing-based intuition, you don't have to, but I'm just throwing it out there if you'd like to think a little bit of statistics, like I was saying with chi-squared earlier. Under suitable normality assumptions, so if we have some sort of Gaussianity assumptions under our QL, then we expect HBL to be approximately chi-squared with 1 degree of freedom. So we could actually get a true distribution on this if we look asymptotically. Kind of a fun thing to think about. I didn't pursue it, I just made it a footnote in the paper that we published on this, but still, it's kind of fun to think about. And so, one thing I wanna bring up is that we came up with a multi-layer extraction algorithm, but I'll be the first to admit that I think we can come up with a better algorithm. So this is something that I would like to improve upon, because right now it's a little slow, slower than I want it to be, but I'm working on it. So this is something that could use improvement. But the basic idea is to look for collections BL that are a little large, that are large, have large score. And so here we just start with vertex neighborhoods as seeds. So we're going to do a seed-based approach, and it's going to be parallelized, right? So we start with a seed set, and then identify its strongest kind of proximal group that has a really high score. And we do this over many, many seed sets, and then identify the ones that are largest with a set overlap. So the basic idea is to alternatively iterate until a local maxima is reached. And here we can say, given a collection, so a vertex collection, we update our layer collection via rank ordering. So this is actually a really natural and fast step. But then the hard step, just like any community detection method, is the following. Once we have a layer set, then we want to identify now, update our collection of vertices via some greedy search. Okay, so we do a greedy search that's a 1-by-1 switching. That's a little slow, I'd like to work on that, but I think there's a lot of available algorithms to do that. And then finally, refinement. So we're going to do this over many, many vertex sets. We end up retaining the family of vertex layer communities with the highest scores such that pairwise overlap is less than or equal to some tuning parameter you set, beta. So you can kind of allow the amount of overlap. So for some practitioners that don't want any overlap, they really don't like seeing two nodes in the same, two nodes in different communities. Sorry, I'm saying this wrong. And two different communities, right? Then we can set that by setting beta to be 0. So let me go through some applications of this algorithm. And then I can touch on the actual theory a little bit, but then kind of leave you with closing thoughts on this. So for applications, we looked at, in this paper anyway, we looked at 3 different applications. So one was a social network, the Australian CS conference network. It has 5 layers, 61 vertices, and overall 620 edges. We also looked at the European air transport system, which is a transportation network, has 36 layers, 450 vertices, and 3,588 edges. And we also looked at an archive citation network. I'll just go over the top 2 here. And in each of these examples, as I was pointing out earlier, we do expect some layer heterogeneity. And it's important to think about, whenever you're applying this, what exactly is a vertex? What does a vertex layer community actually mean? Okay. So we also compared across kind of some of the state of the art. We definitely looked at the Jin Louvain, the multi-layer version of this, as well as the multi-layer version of InfoMap. These are our 2 biggest competitors in the multi-layer space at the moment. And then we had 4 other methods that we looked at, both layer by layer community detection as well as aggregate community detection to see how well we size up. And I was always told never to put a table in my presentation. So for those that are PhD students, it's never a great idea to put tables, but I put it here for your own reference if you'd like to see it. Don't look at it. You can look at me for a second. The main idea, you can go back to this later. I'm happy to share my slides. The main idea here, right, is that multilayer extraction identifies roughly the same number of communities as aggregate and layer by layer, as well as multi-layer. So there's a consistency here among the number of communities that we identify. Moreover, there's kind of a mix of aggregate and layer findings is what and I expound upon this a lot more in the papers. Please feel free to go read the paper. But we end up finding kind of almost something right in the middle of what aggregate and layer by layer would give you. But the interpretation of the layer sets is really what sets us apart. So this is really what makes this an exciting new community section. So I'll give you by picture more of an example of what we found. So in the AUCS network, we identified the following communities. So here's what I did. I took the communities out of the work layer here, which we found the most number of communities, there were 6, and reordered the vertices accordingly. All right, so in every layer. So every layer has now been reordered to match that of work. The communities we found there. And then I draw a nice little square around, by the way, this was manually done. I wish you could do this automatically. If you know how, please let me know. But anyway, so I did this manually, and I just looked at, okay, which of these layers actually have that community? And so what we identify is that for this first community, let's see, there we go. For this first community, we see leisure, work, and lunch are all associated with one another, right? So what you could do, like in thinking about this from a vertex layer perspective, is go back and say, what do leisure, work, and lunch all have in common, right? Just start to think about the commonalities there. So this layer information is actually telling us something. Moreover, so this green one we found persisted across leisure, work, lunch, and Facebook. So these were kind of friends that were also socially friendly with one another, right? So we add in Facebook there. And the same is true with this red block, right? So it's quite a large block. They did hang out, they ate lunch with one another at the conference. They went to go get beers with one another or whatever it was that you want to do after the conference. And they also worked with each other, right? So you can see they also knew each other on Facebook, or they became friends after the fact, you never know. But okay, and now something else though. So commenting on sparsity overall. Our algorithm did not have enough signal, though you can still see structure, but we didn't have enough signal in the co-author network to actually identify these communities. Yeah?
Just because there weren't enough co-authors to do it?
So the score wasn't large overall, and I think it's because of the sparsity of the graph, to be honest. Because modularity as well, like if you start to get into really sparse graphs, has a hard time identifying these communities, right? And again, I'm not just creating a partition, because if I did create a partition, I mean, you could see what would happen, right? You probably see this up here, this, maybe this one, and this one, right? But then this would just kind of be a blank, not really anything going on down here. Yeah, another question?
So I'm really interested in like demographic data, and looking at this, I was like, well, and I do agree with you that at a certain point you can just go into theory and explain anything. So how could you go like, what if you were to know like the gender of the group or the ethnicity? Could you then explain it that way, or would you need like, or does that go to that question again of, well, now we're just adding layers to?
Yeah, so the answer to that, my short answer without knowing exactly how to do it would be, I think there's a way of doing it. So I'm gonna say, yes, you can solve this problem. Immediately from the clustering analysis, maybe not. But I think it all depends on the model and the objective function you set up, right? So we were just looking at modularity, which had only to do with structure. But if you incorporate nodal or layer covariance, you can do that pretty quickly, actually. And there, like I said, there's some work in that. The covariant assisted spectral clustering is one such thing. And then there's also, what was the most recent thing I'm thinking about? Well, I don't know the name of the paper, but this guy, Con Lee at UC Davis, that's worked on a paper here too. Yeah.
I'm curious if your method can also help in some ways overcome the modularity resolution limit problem, because as you were saying, if you just did it on the co-author network, you would either get nothing or you get something weird. But if you sort of apply the communities that you find from the other layers, you sort of overcome the resolution limit problem in some ways.
It's a good point, and you know what's funny is I haven't spent much time on trying to prove or disprove the resolution limit. Admittedly, mostly, and I'll show you in a second why. I think more so from the block model type situation where you assume you have a weak block model. What exactly can you actually identify? But I tend to agree with you. I think that the resolution parameter, especially, and in fact, I think in modularity, even when you're making partitions, right? So with classic, like Jim Louvain or those types of algorithms, I think you can overcome the resolution limit. And you especially can if, again, you assume the same community structure in each layer. Because at that moment, you're saying, well, you may have one weak situation, but you're going to have plenty of others to add to that. So you'll get past the sparsity constraint. So, 10 minutes, thank you. So yeah, you can get past it with enough borrowing of strength across layers. But admittedly, in this paper, I did not look at that. Yeah. Other questions? These are awesome. I love being in a network science class. This is great. Yes?
Could your layers be time frames?
Yes, they absolutely could. I'm not taking into consideration the dependence between each step. In fact, that's my future work, and I'm working on that now. But yeah, if you have ideas, let's talk. But I think that's interesting because you can incorporate a new dependence in the null model, right? So in the configuration model, we had independence among each one of these random graphs. But if you knew it was time dependent, then you could build in a correlation between graphs, I think. Yep. Great. All right, so now getting back to the European air transport network. So this one's a little bit more difficult, had more layers, more vertices. And so here what I want to point out is that there were, and in clustering, this is what always happens, right? You have some sort of benchmark that can help you get through the day. So you're like, well, I'm going to identify communities, but if I don't have any kind of label on these at all, then I really have no idea what I found. We're kind of running a bust, right? So every community detection algorithm you'll ever run, at least when you're trying to come up with a methods paper, will have some sort of classifier at the end of the day, right? That you can go back to. This one has a nice one. The layers here are in fact separated, you would think, according to airlines, major, regional, low-cost, cargo, and something noted as other. And here again, you can go back to the table to identify this, but essentially we found, so ME, Multilayer Extraction, identified 11 different communities where there were on average around 4 airlines and around 12 airports. Right? So again, the vertices here are airports, the airlines themselves are the layers. Single layer, so then we can compare that. But the idea from our results, and I'll show you a picture of it, is that the results suggest that airlines follow distinct routes containing a very small number of unique airports. Right? So that's an overarching kind of conclusion here. But then there was even more to it. So one thing you can try to do is say, well, let's take the actual layers. So again, going back to the layer information you can gather from this, and then look at the communities, right? So we identified 11 communities. Here are the different layers that could have possibly been in the community. And then I separated them, again, hand drawn. I separated them according to what class they were, so I ordered them in that way. And now the color of the block for each one of these gives a representation of the overall strength of the community. Okay? And so what you see, first of all, is that layer sets do closely match airline class. In fact, we can get quite a good match on that. So you can see, for instance, community 3, we have one that's in regional, but then and one in low cost, but then mostly major, right? And then again, we have mostly regional here, mostly low cost here. We could go down that path. I mean, I'm actually calculating a number for that. But then one thing that caught my eye that I thought was interesting, and I think this could be benefit of looking at such analyses, is that there were actually 2 airlines, one regional and one major, that appear in 4 different communities. And so that one is, NAX and SAS. So NAX here, and then SAS as well here. So you can see that these 4 communities each contain each one of those. And you might ask, well, why is that happening? Is my algorithm wrong? Did I do the wrong thing? But then it turns out that these were really the only 2 airlines that went to Norway, right? So they were in a certain region. So yes, they shared a lot of airports, in fact. But that's cool. I mean, so that's cool that we can identify that. We don't expect perfect separation, but when we do see something that kind of meshes here, you have to wonder what exactly is causing that. So the whole point here is that this layer set identification gives us more insight than vertex sets. All right, so now I don't have time for this, which is perfectly okay, but I'm happy to pass along the notes to you. But I just want to at least comment on what exactly can we look at theoretically. So the big question would be something along the lines of, can we guarantee asymptotically that maximizing our derived score function, so we had to do some work to come up with that score function, is the right thing to do under a graphical model with predefined community structure. And so what we end up using is this thing called the multilayer stochastic block model, which is a random graph that directly models community structure. And our approach is to compare the random optimal sets. So we're saying if we have a block model and we identify the score of it, so this would be a random variable now, so I put a hat above it, then how would overall our optimal scores do if we maximize our score? And so how does that match? The moral of the story, so since I know, alas, I'm out of time, so this is always one of those theorems you have to put in there, and you can always go back and look at this to lay it down. But I also always give an interpretation. So here we go. So the interpretation of our results. We found 2 different types of results. One was we have vertex consistency, so vertex layer consistency, but we also have layer set consistency, which is kind of a new way of looking at this. So we're trying to say we have both and jointly vertex and layer community consistency. And so the whole idea here is that we can show that under the MSBM, so the multilayer stochastic block model, that our method, if we maximize our score, will in fact identify consistent blocks of vertices if and only if the following is true. So you can imagine in a 2-block model, if we looked at the likelihood of connection in the first community and the second community, and then the likelihood of connection between the first and second, right? That we just rely upon P11 times P22 to be greater than P12 squared, you can say, which makes sense. So we're saying it's assortative, right? So we're just getting to the point of overall we have, this is a fairly common constraint on being able to identify consistency. We're just saying that we need more signal in P11 and P22 once you take the product than we have between sets. Okay. And then we actually go a little bit further than that and can show, so this joint vertex layer optimality. This is what took a long time of my PhD career. I was working on this during that time. Was we could look at overall, when do we get optimal layer sets and optimal vertex sets, and we identified exactly when we have the score that we came up with earlier. So we had to motivate where did we come up with our score, and we can actually do that under the block model as well. So I also give an interpretation here. What we're looking at is this case where our normalizing constant was just the size of L, and we just say that overall our layer set and our vertex set is going to be optimal with high probability on this collection. Okay, so I know that was a quick way of going through the theory. Again, I'm happy to pass along the slides if you're interested. I could go through simulation, but I think I'm out of time. So for future work, as some have already mentioned, it would be great to incorporate dependencies between networks. So for example, dynamic networks. And that would really build in whenever you're looking at the null specification, I think, because you're just comparing what you observe with what you expect. Also think about weighted networks, and I think it's fairly straightforward to do that, because modularity really doesn't depend upon unweighted networks in this case. We just have to think about exactly how to do that. But then, furthermore, applications in network neuroscience. So a really big area that I'm trying to work on is saying, well, are there consistent subgraphs within brains of different types, right, with different clinical outcomes? Great. Thank you. Thank you again for having me. And I do want to point out there is R code. So if you want to try it out and run it on your own algorithm, I have it there on my GitHub site. I'm working on making an R package as well. That's to come later this semester.
So do try this at home.
Yes. And then email me if you have issues.
Exactly. So maybe we could take like one more question so that we can end on a question, but then I think our official end time was 2.
Yep.
But then we can mingle. But why we at least take one more question, or we could mingle.
Or we just mingle. Yeah, that's okay too.
We could mingle. We have a nice complex network right here.
Absolutely.
So again, thank you very much.
Thank you.